Okay, so in this video, we're going to be looking primarily at missing values and imputation. And in that context, we're also going to be looking at correlation and regression models. All right, so let us get started. We're going to import pandas, NumPy, and Seaborn, all packages that we've used in previous videos. And we're going to be looking at, to start with, two different data sets. Well, actually the same data set, but the missing values are coded a little bit differently. In the first data set, the missing values are just blank, whereas in the second version of this data set, the missing values are coded as out of bounds values. That's what the OOB stands for. Out of bounds values like 999 when we're talking about percentiles of cholesterol level or something like that. So they're clearly 999 age as an age. So the values are clearly indicating something, and they're not in the standard range of the rest of the data. So let's go ahead and load both of these files. So the first one, the null values, you can see that where data is missing, you just get an NaN because there's no value in the data set. On the other hand, if we look at the OOB values, we see that where there were NaNs in the other version of this data set, there are 999s in the updated version, in this alternate version of the data set. And actually in the income column, we can't see an example in the first 20 values, but there is another version of an out of bounds value in the income range. 999 is, at least in theory, a valid income level. And so they actually used a negative value to code up a missing income rather than a positive value. Since, again, in theory, a positive value could just be an outlier as opposed to a potential code value. So we're going to look at what the consequences are in the pair plot if your data set is coded with these out of bounds codes or missing codes for missing things. Then the data set, when you start plotting it, is going to look very different than it would if it just had missing values, because the pair plot will generally ignore missing values. Now, some functions in pandas will, or in Python in general, will not ignore and missing values, and so you'll get errors. But in Seaborn, they will ignore the missing values, and they will just create a plot of whatever is available. So we can see some differences in the pair plot when we go ahead and plot things that have missing values versus things that have out of bound values. So if we plot the one where the missing values are, it's thinking. So the missing values, we can see that there's not a lot of relationship between some of these variables. Again, person is not really a variable. You can see it's uniformly distributed. Age, also kind of across the board, but there does appear to be a relationship with age with our final value, which I believe is blood pressure. Yep. Alcohol. So these all look sort of like normal scatter plots. Again, not a lot of relationship with each other, with interior variables, but there does appear to be some relationship with the main variable in our data set, which is blood pressure. And this looks like a perfectly normal pair plot. Now, if we go ahead and we plot the other one that has the out of bound values in it, you'll see something that looks quite different. So we see these values plotted kind of off to the side. Some of them are much larger than the rest of the data set. And you can see that all the data is kind of squunched off to one side, and then these out of bound values are all plotted out here. And so you do get this weird behavior. Here's what used to be our age histogram. It's now all over here, and the 999s are all over here. So the distinction between this one and this one is what's going to sort of should trigger your initial sense that there's a thing going on here, and we definitely need to investigate this further. Now, typically data sets that have out-of-bound values like this as codes will include a code book that tells you what those out-of-bound values stand for, and many of them, like the census does this, for instance. There may be multiple different codes that you have to deal with. Now, in our example data set, we either have a value or we have an out-of-bounds value. And so it's just one code that we have to deal with for our example. But of course, if you have multiple codes, then you would have to do the same thing with all of the codes. Now, what we're going to do is we're essentially going to create a filter, and anywhere we have, and we're going to do one variable at a time, anywhere we have in our out of bounds data frame, the data frame one, anywhere we have alcohol equal to 999, we're going to convert that to an NaN value. So this is what we needed the NumPy for, was to pull in that not a number value. And what we would have to do then is we would have to do this for each one of our variables. So if we look in alcohol now, instead of having our 999s, we have NaN. And so then we would repeat this for age, income. We would have a slightly different value, out of bounds value we would have to take out, which is the -1. In exercise, we would change this exact code up here, take out alcohol and replace it with exercise and smoke as well. We don't have to do blood pressure. Blood pressure is the variable that we want to predict out of this data set, and everybody does have blood pressure in this data set, a blood pressure value. And I should mention these are not actual like blood pressure values. These are percentiles of where they rank on the population scale. But we would have to redo this for each one of our variables to remove all of these values, and then we would be able to have our data set look exactly like the one that we had before with just the null values in every column. So that's how we would go ahead and we would address those out of bounds values. We would remove them from the data set and replace them with missing values. Now, once we've done that, then our two data sets are going to look exactly the same. Now, before we try to decide whether we're going to remove the null values from the data set and continue without them, or whether we're going to decide that we want to impute those values, so find a best guess replacement for them, so that we don't lose a lot of data. We want to find out exactly how many null values there are in the entire data set. So returning to our data frame that has all the null values filled in, we can use the function, the operator is null, in order to find out whether or not anything in the age column is null, is missing, and then how many of them there are. So there's actually 104 people in the data set that do not have a value for age. For income, there's 31. And the original data frame has 1,000 observations in it. And so what you would generally want, if you want to be able to just simply eliminate the missing values, is you would want the total number of null values to remain generally less than 30%. That's sort of a rule of thumb. In our case, when we add up all of the different null values, we actually find out that it's more like 38% or something like that. And so this is too many potentially missing. And again, these are not, the whole thing is missing. This is one observation is missing for each person that is in the data set. So if we were to eliminate all of the missing data, we would actually have to still eliminate 38 people. We don't get 38% of the data set. We would not get any benefit from having multiple missing values for the same observer. So in general, again, this is going to depend somewhat on how big your data set is, and if it's very small, even throwing away a couple of values can be a problem. If it's very, very large, you may be able to get away with it. But the more null values that you delete, then potentially you can create biases in your data set. And so you would want to explore and examine the null values that you are removing to make sure that they don't contribute additional biases to the data set before you remove them. Now, one method of imputing missing values so that you can preserve the values is the mean. And so we've seen how to calculate the mean in a previous video. What we can do with this operator called fill_NA is we could actually, anywhere in our mean column where we have a value that is missing, we can fill it in with the mean of our data set. And rather than just replace the age value, because we want to preserve our original data set, I have created a new column, age imputed mean, for my data set so that I can tell the difference between the original age values where the data is missing and the column where I have all the original age values, but the ones that were missing have been imputed with the mean. I could also enhance this a little bit with a rounding scheme so that I'm not keeping all of these decimal places, but that's fine for our example purposes. So here we have ages. Everything's been converted to float now because I have one float in the column. And so you have all of these zeros, but then you can see here where my age used to be missing, and now it has been replaced with the mean value from the data set. Now, we can also do similarly, we could do median and mode imputations. Now, the downside of using the mode is that if there is no mode in the data set, you will still have a bunch of missing values. Again, these are somewhat common. Mode is a little bit more common when you have very, very few values, like maybe the number of children. When you don't have continuous data, for instance, or if you have categorical data, then the most common value is sometimes useful to use as a replacement. If we go back and look at our exercise data, for instance, we can actually see that it turns out that exercising 0 minutes a day is a very common response. And so there may be value in filling in 0 for exercise as a mode. Same thing for smoking. When the data is missing, that may be your best assumption. But for something like age, which is pretty evenly spread out, we don't actually have a mode, it turns out. And so when you run the impute as mode function here, it's not going to work. So let's look at our data set. So here's our age imputed as a median. And we can see the 45 is the median. But if we scroll over and look at the mode, it's still NA. This is our age imputed mode. We still have NAs because there is no mode in our data set. So again, mode can work perfectly fine in certain circumstances, but if there is no mode, then it's not going to work. So probably a good strategy before trying to do imputation with the mode is to make sure there is in fact a mode before you do that. Now, these imputation strategies with the mean, median, and mode are extremely common. They're very straightforward, but they really don't necessarily provide a lot of additional information. They're not, we're essentially using no correlation with any of the other variables whatsoever. And so our best guess is just the average, the middle value, or with the mode, the most common value. Now, another way of doing imputation is to try to do some sort of regression relationship. And the example that I'm going to do here is comparing age with blood pressure. Now, I want to say in advance that when you are doing imputations, if there's a variable in your data set that you eventually later want to go back and predict, like in this one, blood pressure, you should not be building models of imputations with the predictor variable, because essentially you're cheating. You're using your predictor variable to predict a quote unquote independent variable, and then you're using your imputed independent variable to then predict the y variable that you use to impute the missing variable in the first place. So that's circular. That will be deceptive. That will make your model seem better than it actually is. Now, so generally you want to use other independent variables to predict your missing values from other columns. Now, in this case, we don't have to worry about, in this data set, there's only one value missing per observer, per respondent to this data set. So we don't have to worry about having two missing values and having to do something clever in the same observation. If a value is missing, all the other variables are there. I'm using blood pressure here because I did not want to actually do the example that my students were going to have to do in their homework. So I'm doing something that you generally should not do, which is ultimately I want to predict their blood pressure from these other variables, but I'm using blood pressure here to eventually to impute my missing age value. So again, generally don't do that. Use one of the other variables, smoking, exercise, something like that, in order to do your age imputation. But we'll remind you of this as we go through. So here I'm going to use the reg plot just to get an idea of how these two variables are going to relate to each other. The one I want to impute and the one that I'm going to use for the imputation. And so we've seen the reg plot before. The error bars appear to be very, very tiny here because we have a lot of data. But we have this regression line, and it does look like there is a relationship between age and blood pressure that we can exploit. The idea here would be that if there is a relationship between age and blood pressure, then we can use that to get a slightly better guesstimate for what our missing age values might be. Now, if we use imputed age and blood pressure to look at the data, then we can see what happens when we impute with the mean or the median, for that matter. We're going to end up with this bunch of values grouped around the center. And one of the issues is that using mean imputations is you may expand the variability of your data set because there is full variability in your data set on, like it goes all the way down to the lowest value on the left and all the way up to the highest value on the right. But now in the middle, you could have a range of values, which is also more variable than maybe the rest of the data set. And so you may be increasing the variance in your model by using mean imputations. And the idea with using regression imputation is that you may be able to reduce the variability, or not reduce the overall variability, but at least not contribute to it getting much worse. Now, in order to keep track of which values we have imputed, what we're going to do is we're going to create a column of values that are just basically true, false, Boolean values, if in fact our original column of ages was an NA. And so I've created this column called age NA. And again, it's just going to be Boolean values. It's going to keep track of whether my original data set had NA values or whether it did not. And if we go look at this new column, we just see this new column is true, false. Now we can use this then to very clearly look at our plots, and we can color the values as whether they have been imputed or not imputed, so that we can see the results of our imputations directly on our graphs. So I'm going to recreate our previous graph, but now with a hue equals age NA, so whether I had NAs or not before, I'm going to display that on the graph as different colors. And so here we can see really very clearly, these were all of our imputed values that used to be NAs, and then this is all of the rest of the data. And you can see that it looks weird. So it's definitely artificial. And again, this may in some circumstances, especially if there's only a few of them, be perfectly fine. But we had 104 of them that we replaced. And so this may not be the best way that we want to go about approaching this imputation. Now, the way that we can choose the best of the other variables to do our imputation with is to look at the correlation. So we're going to use this package SciPy. We're going to import the stats functions from that package, and we're going to do a Pearson correlation, Pearson R. That's the standard correlation value. This function reports out actually two values. We're only going to take the first value, which is the correlation. And we're going to look at, again, we're using blood pressure here so that I don't do my students' homework for them. But again, you should, in general, use one of the other independent variables to do this as your imputation value. So here we're going to run the correlation between age and blood pressure, and we can see that there is a general trend in the data, which we saw in the graph, a correlation of 0.64. That's not great, but it's better than zero correlation. And when you use the mean, that's essentially what you're doing, is you're using a model that has no correlation with any of the other data in the data set. So another way to calculate the correlation is to use the stats models package, and their correlation function only reports the correlation. So here we're doing the age with the imputed mean age correlated with blood pressure. Now, some of these correlation functions will work perfectly fine if there are missing values, and some of them will break if there are missing values. So you want to be careful when you do these calculations. One package may just skip over the NA values and give you a real value, and others may give you errors. So you want to be mindful of that as you're doing these calculations. So if I calculate the correlation between age and income, again, this version of the function totally ignored the null values because both of these columns have null values in them. That's not very high. It's a little lower, but again, this age and income are independent variables, And so that's actually what we would prefer to use for proper imputing in a model like this. Age correlated with blood pressure. So we can see that this is the unimputed age column, so it's just ignoring the NAs. And so the non-NA values are correlated at 0.67 with our blood pressure. When we imputed with the mean, that correlation dropped to 0.64. That's not a huge difference, but it is noticeable. Now, it's the stats function, the Pearson R function, that is the one that's going to complain if you use NA values. So this is the unimputed column that has NAs in it, and this is the error message that you get. So I had no problem doing it with the imputed column, but we want to know what the correlation is before we do the imputation. And so this particular function is not really going to work very well. So you would want to continue using this other one from the stats models package. Now, one potential issue that I mentioned is that one possible solution to your problem is to simply drop all the NA values that are in the data set. And you can add them up, count them one by one. Another way to do that is to use your data frame, drop all the values, and see how big the data frame is after you drop them using this drop NA function. And when we do that, again, we see that there's missing values because there's a bunch of NA values that have been dropped. We can also look at the size of the resulting data frame. This is now 638 rows. So we had 1,000 rows before. So we have dropped more than 30% of the data set. This is like 30, I guess it's like 36% plus of the data set that we've dropped. So that's bad in terms of, again, the rule of thumb is less than 30%. This is several percentages higher. So this is probably going to end up dropping too much of the data if you just want to eliminate them, which is the whole reason that we're talking about preserving some of the values and continuing with our imputations. Now, we talked about the mean, the median, the mode imputations. Another way of doing imputations, of course, is with regression. And so we are going to import from the stats models package the ordinary least squares regression model. If you need to use logistic regression or something like that, you can import GLM instead. We will talk about classification models in a future video. And then we're going to, in this case, I'm going to create another data frame from our values that will allow me to actually rename blood pressure. Because one of the issues sometimes with these formulas with using column names that have spaces in them is that sometimes these functions, they don't particularly work. You have to do things to tweak them. So I'm going to just rename it to make it a little easier for us to work with. Now, this ordinary least squares model works somewhat similarly to the way R works. And you're going to specify a formula. Here, we're going to model BP on age. So one of the things that to keep in mind here, this tilde is indicating what is being modeled with what, and the Y variable actually goes first, and the input variable, the X variable, goes second. And then we're going to fit that model, and then we're going to print the parameters, the coefficients for our model. Now, if we were actually trying to do the final model for our data set, this is what we would want. We would want to predict BP from H. But in our imputation case, we don't actually want to predict BP. We actually want to predict age. And again, you don't want to use the y variable in your final model to do any imputations. But it's the age variable that I want to eventually impute. So I don't need these coefficients because that's predicting blood pressure. In this case, I want the age coefficient, the coefficients that will take this variable and predict age from that. So age is being modeled by blood pressure in this case. So these are the coefficients I want. This makes more sense. I don't have -6 as an intercept anywhere. I have 26 as my minimum age value, and then multiply my BP by this in order to get my predicted age. So that suggests that as you get older, your blood pressure goes up, which is what you would expect to happen. Now, again, why change the name of blood pressure? Because if you use this version with a space, it's going to yell at you. Now, in R, there are ways around this, of course, but it may just be easier to change the name of the variable. Now, I'm going to create, in this case, a column just so I can see what all the imputed values are of my age. So I'm creating a column of predicted values, and I probably should label this predicted age. Where I'm using my, again, the variable that I used in my model to impute my age values. I'm using BP here, which again, don't use, because that's the outcome that you want eventually to get. We're going to multiply it by the coefficient that we found, and we're going to add in our intercept. And so that's going to use the BP value in each row to calculate the predicted age for that column. And then we can look at those values. And this is just an example. Now, ideally, what you would want to then do is you would want to tweak this in order to fill in the values just with the imputations that you're making from your model up here. So we would want to create in our data frame, we would want to use this fill NA function in order to do our imputation. So we're going to modify this in order to look at it. So what I'm going to do is I don't need both of these. And then what I'm going to do is I'm going to replace, instead of filling in with the median, I'm going to fill in with this. And we're going to use the original data frame, and we're going to use blood pressure. And we're going to change the name mean imputed regression. And then we're going to run that. So now let's go look at our new column. So notice what's happening here is in our new imputation column, we are not imputing every value. We're only imputing the values that needed to be filled in. And each of those predicted values is actually a little bit different based on the information that we have available. And so if we were to go ahead and then replot this data, let's look for our plot. Now our age values are kind of more distributed throughout the entire data set. And while they're not perfectly lining up with our BP line, they are fitting into the data set a little bit more. They're not all piled up on top of the center line. They don't have quite as much variability or spread, and they do a little bit better job of sort of fitting inside our original data set. And that's what we want. Again, we're not going to get perfect, fit, but we want to be able to rescue them enough that we can still come up with a meaningful result from our analysis. Now, again, ideally, and I'm going to keep repeating this, but we're almost done. Ideally, if your final model that you want to predict is going to use blood pressure as the prediction variable, don't do imputations with that blood pressure variable. You would want to use other variables in the data set to do that. So, for instance, you might want to use income to predict age, or you might want to use exercise or smoking to predict age, something like that. You would want to calculate the correlations between each one of the possible independent variables and then impute your missing independent variables with other independent variables. Again, the correlations are not going to be necessarily great. You don't want collinear variables, generally speaking. You want things in your final blood pressure model to not be correlated with each other. You want them correlated with blood pressure, but not with each other. So this will change some of the correlations a little bit, but it generally will not do that much. But then you will still end up, if you're imputing missing values and independent variables from other independent variables, you're still going to have this same set of independent variables predicting your final blood pressure data. It's just that when a value is missing, essentially the result will be a model that has one fewer variable. But rather than building different models for each of the variables that's potentially missing, by imputing the values, you're essentially creating those models by default. So this is the end of our discussion on imputation.